Well, the way we find area under curve, let's say g of x, is we write the integral of that function dx from point A to point B. So we got definite integral that gives us always same thing, which is area under the curve. So I guess that's how we saw it last time. Hi, it's good that we're all here. So analogously, for the other one, for the middle area, we're gonna have integral under that red curve, right? So the area will be, again, integral that starts at A, ends at B, and the function now it's function f of x dx. And these two areas, geometrically, if you consider them, this big one and the small one, could be subtracted. So what you get is area in between if you subtract from the big one the small one. So that's one of the applications of those definite integrals. So you can find the area of pretty much any figure. You just need to see where it starts, where it ends, and then upper minus lower, and that's the idea of the way to find the area. From one curve, you subtract the other and you integrate. So they discuss this here, and as long as we can figure out which curve is above and which one is below, well, then we can find all kinds of areas in between those curves. And that's pretty interesting procedure, because before we could find areas only of rectangles or triangles or circles, but now it could be any function, and that's the power of this process. So, for example, if I try problem number 2 here, I need to decide which area or which curve is above and which curve is below. I'm going to say, Alex, I can see only one curve here. This looks like a cubic function, x cubed minus 4 times x, right? But it's not really the case, because we have also the line that happens to be the upper curve. So if you were to find the area, you need to subtract from the upper curve with equation y is equal to 0 the lower, which is this x cubed minus 4x. And you go from 0 up to this point, and they didn't tell us what this point is. Well, I guess they expect us to find it. So what is the point of intersection in here? Well, it looks like it's going to be a 2, right? And a negative 2, because if you wish to set this equal to 0, you're going to end up with either x is equal to 0 or x to the second minus 4 is 0. So you can either factor, you could just find x by extracting the square root and see that's either plus or minus 2. So integral that we consider is from 0 to 2, because that's the area they want. They don't want to touch negative 2. So it is important to know the graph, or if you don't know, to actually produce the graph, to be able to see what is your upper and what is your lower curves. So then you can try to integrate. And well, if I disregard 0, it means really nothing here. I should probably distribute negative. So that's what I'm trying to integrate. in reality. And then use my favorite power rule for antiderivatives formula, x to the 4th over 4, right? Add 1 to the power of x, which is 3. And if I add 1 to the power of x, which is 2, I'm going to get something like that. And now we go from 0 to 2, and we'll be able to find this area. Please notice that at 0, if I plug in now 2, let me plug it in careful, 2 to the 4th over 4, subtract, now I can cancel, I got 2x squared, so it's actually plus 2x, 2 times 2 squared. And then we need to also subtract values at the lower, and notice that at the lower, I'm going to get just zeros. And that's why 0 is my favorite number when I work with definite integral, because this whole thing disappears at 0. So 16 over 4, that'd be something like 4 plus 8. So notice that the answer is 4 for that area. Please notice if you did not go with upper minus lower, then the sign of this entire expression would change and it'd be not positive 4 but negative. But since you're looking for the area, you need it to be always positive. So yes, integral could be negative. It all depends, because integral, definite integral, is not always the end. But if you want to find the area, well, then we need to go with upper minus lower. That's a little extra what this section is giving us here. It's a little extra about using integrals to find the area, because it's actually antiderivative. That's what it is, but it could be utilized in finding areas, and that's what makes it be pretty interesting. So those exercises where you have areas in between curves that you need to actually graph, let's say problems number like 19 or so forth, actually the ones without pictures, starting at problem number 5. Well, for those, you need to get plenty of room. So we'll, I guess, get a little board and do the problem so we have enough room. So let me do this. Share board. So let's do a couple of those for fun. I think they're pretty interesting little exercises. So how about the exercise like number 6, for example? In this problem number 6, they give us 3 equations. First of them is x squared, the favorite parabola. The second is negative x squared. Okay. And the third is line with equation x is equal to 1. And they also say it should be bounded by these 3 curves, and that's it. So let's see what picture tells us about this story, because they didn't tell us the limits of integration. They just gave us, looks like, one parabola, the other parabola, and then they also give us x is equal to 1 line equation, right? So positive x squared opens upwards, negative downwards. Remember, we worked with parabolas for a while, right? And now I can see from this picture that actually they deal with my favorite number 0. And another point they working with is 1, because it's x is equal to 1. So my definite integral will go from 0 to 1. Now I need to know the upper curve. It looks like the upper will be my x squared, the favorite parabola. And this one will be the lower curve, negative x squared, right? So I need to subtract from the upper the lower. and this will end up being x squared that I have to subtract with negative x squared. And you say, so they're gonna cancel? Not really. They're actually gonna be added, right? So you're gonna end up integrating 2x squared. Oh, that's a nice integration. Well, it looks like I got lucky because I got my favorite 0 for the limit, right? So again, I add 1 to the power of 2 and put that same in denominator and go from 0 to 1. And this gives me the answer, looks like 1/3, right? So you get 2 times 1 cube over 3 minus 2 times 0 cube over 3. That one is 0, so we get 2/3. That's the area. Notice that these curves, these parabolas, they curvy, right? But the area in between is 2/3. It's a nice little fraction. Isn't that amazing? So let's do another one. Interesting exercise, right? So for this one, I didn't really need much room. Well, that's just a beginning. Turns out these exercises are rather tedious. So sometimes you need to struggle a little bit. Let me try number 13 exercise. That might be worse looking. In fact, some problems may look pretty much the same, but when you start doing them, it might take you 5 times the amount of time spent on them. But technically, the process is the same no matter what curves you have. All you need is to find the upper and the lower, and then where they intersect each other. So you'll be able to set up this integral and then take it. But again, depending on the points of their intersection, those curves, it might be tedious to actually perform that. So I guess, first of all, to graph, I will use the points of intersection of those curves with my x-axis. In other words, I'm going to set both of them equal to 0. That's how we find x-axis intercepts. So y is 0, and then we factor. So from the first one, I take out x squared, you get x minus 3. So x is either 0, order 2, or 3. If you remember order, the word that deals with the power of x, just like when we have a graph of parabola. Remember, order 2, 0 means it's just touching our x-axis. In other words, when I try to graph this first equation, there'll be 2 points of intersection with my x-axis at 0 and at 3. And then at point with a cubic parabola, so the one that I have has degree 3, so one end of it goes upwards and the other down. So that's our goal. So the way it looks, it crosses at point 3, this function, and then touches at 0, and then returns back. So it's like that. So it just touches. What about the second one? Well, again, I'm going to factor out my letter x. So we got a 0 again, or negative 5. So let me grab this in blue and see what happens. There are 2 points, negative 5 and 0 for the intersection, and that parabola opens upwards. So what's the region that I need? Well, I see one here, and that's what we're gonna need to find. So first of all, I can see which one is upper, and this will be the first one. So when I set my integral, I have to put the upper curve minus the lower curve, and the upper will be x cubed. Subtract 3x squared. And then I need to subtract the lower from it, and the lower will be that parabola here, right? The blue one, x squared and plus 5x. But that's not it. I need to know my limits of integration. I already know one looks like it's a 0.0, but what about the other? Where's the other intersection? And it turns out I need to solve a little system. Let me write this down below. So system of these two equations finds the solution of system, finds the common points, the points x, y that belong to both of these equations. So you just put them in a system and subtract, so you eliminate one of the unknowns like y. So when I subtract, the x cubed will stay, right? And then the signs of terms below will change with the opposites because I'm subtracting. So I got two like terms, x squared, and they will give us -4 of these x squared and plus 5x. And again, I need to solve another little equation by favorite factoring. Take out x. And second factor be x squared minus 4x minus and plus 5. You see, it's getting real lengthy. And it just brings you to area with lots of algebra. And in a calculus, we, well, just need this integration. So we need only to know the limits, upper and lower. So that's why I have to spend so much time doing algebra. And when I factor 5, x squared is my favorite factor, x times x. Now, sign is minus, and so is the other sign, minus, right? Because, again, it's 5x, and there's just 5, so it was not careful. So, what is going on in here now? Well, looks like I wasn't careful when I wrote down this sign because it's a +5, so it has to change with a -5 when I subtract. See, that's why I need to be factoring this with not two same signs, but one minus the other is plus because we need to get -5. And then I go 5 times 1. So you can always fix it. You misprinted something. So it turns out that these two curves will actually intersect not at 2 places, but at 3 places. How about that? There'll be another intersection that I just discovered. Look at that. So I wasn't careful when I produced the graph, but we will fix it. See, algebra always gives us ideas of what is going on. So I have to fix it a little farther. And that's going to be another piece because that cubic function starts to grow faster and actually goes to 5 where they intersect. Maybe I can actually try to clean this because it's not as obvious. So I better draw this a little bit more careful. But how would you like that? I was trying to make a picture and discovered the fact that these two actually have another intersection. Another intersection will be at 0.5. So there will be another integral. There will be another integral, another area that we have to find and add it together to get the area in between these curves. And this will go from 0 to 5. So my first one goes from -1 to 0. This be my integral here down below, right? And the second one will go from 0 to 5. How about that? And notice that when we have second integral, the upper will be the blue one. the upper will be this blue parabola. So they interchange their positions, those curves. How about that? You see, this seemed to be a pretty challenging exercise. Well, I would say this is standard, and that's another reason why I don't get much into the applications, because we end up solving same kind of exercises, but they get real tedious. That's the only thing. And instead of being stuck with all this simplifying, I'd rather just show you how we do calculus instead of we solving systems of equations. So it actually puts everything together, everything we learned in all the math classes. So now, before to take these integrals, I better simplify them a little bit. So the first one is x cubed. Now, here's the sign change, right? -3 minus 1 is -4 x to the second, and then there will be minus 5x. And for the second integral, it's always going to be the same, but with the opposite sign. So you can put minus x cubed. See? Here's plus, they put minus. Minus 4x squared should be plus 4x squared. So they always change their signs. And plus 5. Why? Because we interchange those curves. We subtract vice versa. So you can verify if you want. So here's minus x cubed. The 4x squared, so two minuses, 4x squared will give you a plus, and another x squared is 4. And finally, there'll be a term with a 5x. It used to be minus 5x. Yeah, lost x. Shouldn't do that. And this is plus 5x. Okay, so now we discovered everything. And then we also have these little limits to make sure that we plug them in. See how lengthy this becomes? I say that's fun. But indeed, if you'll be able to do this one exercise, then you can do just about anything here. So that's why I selected number 13. So some people may not like this number, and it fully deserves that. So the good thing is that now we're gonna take those integrals. So let me take the integral number 1 here. Antiderivative will be, let me write it somewhere here, x to the 4th divided by 4. So what I'm doing, I'm working with this x cubed. Now next is going to be minus 4x squared, so it'll be minus 4. The power is added, so it's x cubed over 3, right? And then finally minus 5x and then squared over 2. And I go with this from -1 to 0. Okay, so that's a good start. And I plug in 0, and then I plug in -1. But I want to simultaneously do the other one because it'd be a same antiderivative, but with opposite signs. So you don't have to do it again. You could just copy what you have above, since terms are the same, but the signs are opposite. So you just change signs. And after that, it's going to start to be different because you have different limits of integration. Well, at least 0 participates there. So at 0, I don't want to waste time. I'll just put zeros everywhere instead of x here, here, and here. So it'll be just a 0 minus. And now I need to subtract value at -1. Okay, so let's see what this is going to be. -1 to the 4th over 4 minus 4 times -1 to the power of 3 over 3. So this -1 simply changes the sign if you have odd power, and that's -1 power of 2. Okay, so there is a negative in front, and we get a quarter. I would highly recommend to use a calculator here. Plus 4/3 and -5/2, right? So these 3 fractions with common denominator 12, you need to put together. So let's see how many 12s this is going to be. Here's 3, here's 4, and here's 6, right? So you get a -3 and 16 is 13. and minus 30, 13 minus 30 will be minus 27. Oh, minus 70. Okay, minus 70. So we've got one piece in here, and that's a great start, looks like. So now we're gonna get the second piece, right? So what will be the second piece? Well, looks like I need to do the same thing again, and the good news is that again we have a 0. It's my favorite little friend, because otherwise I wouldn't have enough room here to do this whole thing. So let's try. Minus 5 I plug in to the force, right? And oh, there is one thing, that's what I'm looking at. I forgot that there is a negative. You see that negative? Say, Alex, I see the negative. So change your sign. So it's positive, because it should be positive, because this is here. That's why I started to wonder what's going. Well, because there is minus that will kill that negative. Okay, now it feels much better. So 4 here, then now notice that this will be positive because that's the upper, right? So then 4 times 5 cubed. This is a little bit more tedious because number 1 or -1 are the nicest numbers to plug in. Once you plug in something like 5 or especially fractions, oh, that's going to take you a little bit of work. But again, the good thing is it's analogous to the previous. So that's upper, and then lower will be my 0, right? Because when I plug in that 0, everything disappears. So we're going to have to utilize same denominator, which is looks like 12, right? So I'm going to get them all to 12s. So I'm going to need to use the other color. So it'll be like 3 and then 3. That's how I get 12 in the bottom. Here's 4 and there's 4. Another 12, and here's 6 and another 6, right? Okay, so let's see how many 12s we're gonna get. I'll put it like that. 12s. 5 to the 4th is 625, right? So 18. See, I better use a calculator here, because if I put a negative sign, don't forget. 25 times 25 is 625. So 325 is 75, and 1875 is my first one. See, that's a big one. Okay, minus. Now I need to multiply 5 cubed by 16. Oh, that's another big number. I can just write it 5 cubed times 16. And finally, add it with 5 cubed again times 6. Okay. So what is this equal to? I guess I better use a calculator. In fact, if you use a calculator, the calculator doesn't really care what you're trying to calculate, right? But for you, might easily make a little miscalculation, and that way you will definitely get different answer, right? So that's why I think it's good to get a calculator. 5 times. I'm just trying to write it down, because when I go to look for my calculator, the page will disappear, so I won't see what I'm entering. So scientific calculator. So let's enjoy it. Minus 18 times, no, minus 1815. 1815. I guess I got that right, I hope. Oh, no, not 1575. See, I have pretty weak pen. So it's just try to trick me. 5 cubed times 16. And another 5 cubed times 6. So you could just factor out 5 cubed and do 15 plus 6 if you want to help your calculator. But a good thing happened. We got 875, and it's still divided by 12. So let me go back to that picture. Oh, what a mess, right? 875/12. They're both positive, so that's already a good sign. And then we need to subtract these guys, right? So the second, add these guys, right? We have to take one plus the other. So the other was 875/12. It's good to have them both as 12s. And the first was here, 17/12. Okay, so when you add these together, I can put it like that. Add them together, the answer will be 892/12. You can divide using calculator and get the actual area if you're really interested in this, but I guess I got so happy that I was able to add them that I guess I'll stop at this stage. So what's the point of doing such a heavy arithmetic? I don't see there's a big point, and that's why I always recommend to my students to use their calculator to get help doing the exercise, because problems in this section, they are pretty tedious. And now you can see the reason why I was trying to avoid lots of applications, simply because you always end up with some kind of mess. And that's why I'd rather do kind of the same problems, but with a nice and nifty looking answers. Oops, that's statistics. And rather than just messing up with this tedious arithmetic, because and it's always there. So there is not much you can do. And that's why I just wanted to do a problem to illustrate you that these areas are doable. And of course, they're utilized a lot in various areas whenever you need to integrate one of these functions. And I don't think I want to give you any more hard time. I already, as promised, tried to show you one exercise of this kind, and the others will be analogous. So maybe a little later I'll show you another one. But again, I don't want to concentrate all the time on some tedious exercises and turn this class into the engineering class, because that's not what we want to. But main idea is to show where the topics of integration and differentiation being used. So I did one with integration, and as promised, I'll show you maybe next time or time after next the use of derivatives, and that'd be, I guess, our goal. And right now I'm looking for the section where we can find the more applications of integration, because turns out that with antiderivatives, it's really not that simple as with derivatives. And that's the key difference. And that's why the next chapter is working on more various cases finding the antiderivative. So I can just continue a little bit more with these using additional topics of antiderivatives. When you cannot take the particular integral for whatever reason, what should you do? And it turns out there is an analog formula for the derivative of product. So let me get there. And this formula says if you, so let me share screen. If you have something like exercise number 1, for example, you cannot really take it using substitutional methods that we already observed in a previous chapter. Turns out that the way to go is use special formula that says integral of product is equal to product of these two minus integral of, so if you integrate u times dv, see, dx, u times dv, then what you need is to go uv minus integral of vd. So what is that? What does that mean? Where it comes from? Well, if you have a derivative ddx, they like dx, of a product that I used to write u times v prime, so that's probably what you might remember. It's u prime v plus v prime u, right? That was the little formula. All right, to write u, just letter u. So this formula we used a few times, and turns out you can write this derivative a little bit differently. So you can write it like that, ddx. So when you write this formula with derivatives, so it'll be du over dx times v plus dv over du, so dv over dx, sorry, times u. So that's the same thing. See, it's not the way that is convenient to write. That's why I always try to avoid writing our derivative, let's say, of u as du over dx. But it's function of x, so it's du over dx. So what you can do now is cancel this dx everywhere, so you multiply by it, and then you integrate both sides, so every single piece. And then you can notice that if you take derivative and I'm talking about the middle term, derivative of this, and then you integrate it, then derivative and antiderivative disappear, and that's where your uv is. So it's really common as a formula that we have here that we already utilized, and that's the point of the story. So uv is going to be here, the first term, and then you bring over to it this piece, so that's how it goes with a minus sign, and what's left on the other side is integral of u dv, which is exactly my first term. So you can give it a little thought if you want to, but the point of story, it's the same as a formula for derivative of product. And now I'm going to do standard steps, and I'm going to do it a couple of times in a couple of exercises, so you start to get used to it a little by little. So u and dv are here. So instead of u times dv, I have a replacement. So instead of x, I use letter u, and instead of e to the power of minus x with dx, I use my dv. So once we set it like that, the first piece I'm gonna find derivative, and the second piece I need to find the antiderivative. So I take derivative, so I get a 1 times dx is equal to 1 times du. Please notice I need to know what du is. And then integral for the other will enable me to find what is letter v, because integral of v is, of dv is just 1 dv, so it's just letter v. And then what's the integral of e to the power? Well, that's the same thing, right? But then we need to have a negative sign next to it, because when you take derivative, the chain rule will make this go away, right? So anyways, I'm gonna now set up whatever we have in the formula above in such a way as here's our ingredients, u times v, u times dv. So what is u? That's x. Now I'm going to write everything in terms of x, and then I will be able to get the answer. That's the point of use the formula. Plug everything in it. What is dv? Well, it used to be here in blue without the integral sign. So it's e to the power of minus x, and that's it. And then that's our udv, right? That's our, at least that's your original integral. Yeah. So what it is equal to? The integral of that. Well, u times v. So now I need to multiply my u, which is x, by v, which is negative e to the power of minus x. Whatever it is, I just multiply by it. Subtract. Now I need integral of v, which is minus e to the power of minus x, times du, and du is same as dx. So instead of the integral that I had here originally, I have the difference of two pieces. So first piece I don't need to worry about because it's already without any integral. For the second piece, I have here two minuses that give me a plus. And notice I just took the integral of e to the minus x. It's very often that you kind of repeat this again, and you get minus e to the power of minus x, and now I put plus the constant. So the point of story, the integral that has a product of two, just like a derivative that has a product multiplication of two functions, I'm able to integrate by parts. That's the process. So I'd like to do one more, and then it'd be same pattern that you're going to utilize in all the exercises. So my goal today is to start with this process and make sure that you can see that this is exactly the same procedure for all of the exercises that you encounter in this little section. So for this matter, I can try to do problem like number 5 with ln. T times ln of 2t. So now letter t, it doesn't really matter to us, x or a t, right? And then ln of 2t and dt. So it turns out that one piece I find the derivative, right? And the other antiderivative. So I can only find derivative of ln, and that's why I call ln of this as my u, because that one I will be differentiating. Because integrating ln will be, maybe next time we'll do it. It'll be tedious. So if this is my u, then for dv, I'll put everything that remains. U times dv. So we're going to call as a dv this entire remaining t times dt. So this is my nice little start. So now I take derivative of ln. Remember, derivative of ln of x was 1 over x, right? Okay, so we're gonna do same thing with ln 2t, so that'd be 1 over 2t, but chain rule says Alex times 2 and attach dt to it is equal to d. So we got ourselves a nice little start. Now the other piece is even nicer when I start to integrate on both sides. The antiderivative of v of dv is going to give me v, right? And antiderivative of t to the first power will be t squared over 2. And now we're all set to use this red formula once again. So I'm not going to copy the left side. I'm going to just write this uv minus integral of v du. Let me write it here. U times v minus integral of v du. And that's exactly what we have here. All of the ingredients in this brackets. So first is u, and this is ln of 2t. So I just copy them where they are, times v, which is t squared over 2. And that was a good start. Now I go with a minus sign, and now I need to know what is integral of v du is. So that's the part that I need to actually work with. And notice that v is t squared over 2 and multiplied by du, which is dt over t, right? And please notice that this one I can find the antiderivative. So my first one is already part of the answer, so I just copy it, and it's always like that. And the second one, I need to integrate something like 1/2 integral of t dt. So please notice that once again, we happen already to deal with it. So it's very often. Usually people bring this t squared over 2 first, so it doesn't mix with ln. And now we have 1/2 times t squared over 2, right? Add 1 and put that same power and the constant. So doing all of these procedures, I avoided finding integral of ln. And that's the whole point of story. Finding antiderivative of ln. Oh, actually it was here, exercise 5. So I think this is a little bit artificial, right? It's a little bit unpleasant when you never saw it before. And that's why I did a couple of problems of this kind in the beginning of section. And next time I will look at another one or two. So I hope you will start to see that they really are all the same. So the key part is call one as u, the other is dv, and then the process goes, and then whatever pieces you produced, you plug into this formula. And in this formula, there is a nicer integral not of the product, but only of v, and that's usually helps to find antiderivative. So I don't think I want to give you a quiz on this. It's a little bit too much, right? I want to just let you go. You deserve it, right? So I'm going to stop my recording for today.